As you probably know, the ADS1298 is a biosignal acquisition IC designed for applications like ECG, EEG, and finally EMG. It doesn't just contain the analog front-end to acquire the signal. It also includes programmable gain, an ADC, a digital interface, and several other features that let us control the acquisition directly from a microcontroller. But how exactly we connect it to an MCU? And once it's connected, how actually we configure it and get the data out? Before we start, if you're new here, this series is all about trying to recreate Meta's EMG wristband from scratch. We are going to explore the hardware, electronics, machine learning, and everything in between. So if you want to follow the entire journey, make sure to check out the playlist. Electrically speaking, the ADS has quite a lot of pins. But if we are interested in communicating with the ADS1298 from our MCU, there are only a few pins that are really important. First, we have the 4 pins used by the SPI protocol: serial clock, data in, data out, and chip select. Serial clock is the clock generated by the MCU. Data in is the data going from the MCU to the ADS1298. Data out is the data going from the ADS1298 back to the MCU. And finally, the chip select pin is used by the MCU to select the ADS1298 on the SPI bus. Then we have 2 other really important pins: the start pin and the data ready pin. Start is controlled by the MCU and tells the ADS1298 to start or stop the conversion process. Data ready works in the opposite direction. It's generated by the ADS1298 and tells the MCU that a new conversion result is ready to be read. So these are the main pins involved in the communication. But before we can acquire any useful signal, we have to initialize the ADS1298. If we open chapter 10 on the datasheet, Texas Instrument actually gives us a complete procedure for getting the ADS1298 up and running. I'm going to follow this procedure because it's a great way to understand how the chip actually works. First, we need to power up the analog and digital supplies. This part is pretty straightforward. We simply need to follow the power up sequence specified by Texas Instrument. Next, we have the clock. Let's assume that we don't have an external clock, so we are going to use the ADS1298's internal oscillator. In this case, we configure the clock select pin accordingly and wait for the oscillator to start. The datasheet also gives us a way to check that the oscillator is running. If the start pin is tied high, the data ready pin should start toggling at the frequency specified by the datasheet. So even before we are actually acquiring a biosignal, data ready can already give us an indication that the device has started correctly. Next, we need to make sure that the power down and the reset pins are in their inactive state, which is high. These 4 steps becomes much easier to understand if we look at the timing diagram from the power up section of the datasheet. After powering up the device, we need to wait before issuing the reset pulse. The datasheet tells us that the reset pulse should be issued after TPOR or TBG, whichever is longer. TPOR is the minimum power on reset time, while TBG is the time needed for the VCAP1 to charge to 1.1 volts. So basically, we wait until the longer of these 2 conditions has been satisfied. Then we can issue the hardware reset pulse by pulling the reset pin low for the required minimum time and then bringing it high again. After the reset pulse, the ADS1298 needs 18 clock cycles to finish the reset and initialization. Once those 18 clock cycles have passed, we can continue with the configuration. Now we're finally ready to start communicating with the ADS1298 through SPI. The first command in this procedure is sDataC, which stands for Stop Read Data Continuous. This tells the ADS1298 to stop continuously outputting data, allowing us to configure the registers. So at this point, we're not trying to acquire the EMG signals yet. We are preparing the device. Next, we have to choose the reference used by the ADC. We can use either an external reference or the internal reference. For this example, let's use the internal one. The datasheet tells us to enable the internal reference buffer by setting the appropriate bit in the config tree register, and then wait for the reference to settle. Notice that the PD-ref buff is not a physical pin, it's simply a bit inside the config tree register that controls the internal reference buffer. Now we get to one of the most important parts, configuring the registers. The datasheet gives us some example values that we can use to verify that the ADS1298 is working correctly. First, we write the config1 register using this command right here. In this example, this configures the device for high resolution operation and selects the desired data rate. And then we configure the config2 register with this command right here. And finally, the datasheet tells us to configure all the channels with an input short, using this command right here for every channel. This means that we are not measuring the electrodes yet. Instead, we are internally shorting the channel inputs. The reason for doing this is to measure the noise floor of the ADS1298 itself. Now we can set the start pin to high. This activates the conversion process. From this point on, the ADS1298 starts producing conversion results. Before capturing the data, we need to put the ADS1298 into the RDataC mode. RDataC stands for Read Data Continuous. In this mode, the ADS1298 continuously makes the conversion results available through the digital interface. And now we can finally capture some data. The ADS1298 uses the data ready pin to tell our MCU that a new conversion result is ready. When the data ready pin goes low, the MCU knows that it can read the new samples. But the ADS1298 doesn't simply push all the bits into the MCU by itself. The MCU is the SPI master, so it generates the serial clock pulses. For every clock pulse, the ADS1298 shifts another bit of data out through the data out pin. For example, with 8 active channels, one complete data frame contains 24 bits of status plus 24 bits for each channel. So that's 24 plus 8 times 24 equal 216 bits. The MCU generates the required serial clock pulses to shift those 216 bits from the ADS1298 into its memory. Once we have checked the noise, Texas Instruments repeats a similar procedure, but this time with a known internal test signal. And this is important because we are not connecting any function generator to the electrodes. The ADS1298 has its own internal test signal generator. We configure config2 to enable the internal test signal and configure the channel multiplexer, so that the ADC receives this signal instead of the normal electrode input. Now we know exactly what signal we are expecting, so we can compare it with the data we are receiving from the ADC. This gives us another way to verify that the entire acquisition chain is working correctly. And that's basically the entire startup procedure by Texas Instruments. Of course, we don't need to perform all these tests every time we want to measure EMG. And once everything has been tested, our real firmware can be much easier. So basically, after the initial testing, we can configure the ADS1298 with the settings we actually want, start the conversions, wait for the data ready pin and continuously read the samples through SPI. So now we understand the overall procedure. But there's still one important question. How do we actually tell the ADS1298 what to do? If we look at the command table in the datasheet, we can see that every command corresponds to a specific byte or sequence of bytes. For example, if we want to send the sdatac command, the datasheet gives us its opcode. Our MCU simply sends this byte through SPI. Of course, we don't want to write SPI commands like this everywhere in our firmware. Instead, we can create our own functions to make the code easier to understand. For example, this is a function that could simplify the process of sending the command from your MCU to the ADS. So instead of manually writing every byte, we can simply code this method. And this is where the register table we saw earlier becomes useful. The datasheet tells us the register address, what every bit does, and what value you need to write. Our firmware then converts that information into the SPI bytes required by the ADS1298. And that's basically the idea of using the ADS1298 with a microcontroller. I know this wasn't a complete tutorial covering every single register and every feature of the chip, but hopefully now we have a much better idea of how the whole system works. In the next videos, we are going to go deeper into the firmware, the registers, the actual EMG acquisition, and of course the PCB and electronics needed to build the whole system. So if you don't want to miss those videos, make sure to subscribe to this channel. Thank you for watching and I'll see you in the next one.